So, welcome to lecture number 30 of phase equilibria. So, we will just continue with the last part of phase diagrams of alloys and some common metals and alloys before we get into some more aspects of phase diagrams, phase equilibria. So, the first thing we'll do is to just recap. So, in the last lecture we discussed about cast irons. So, we discussed about grey cast iron, in which you can have perlite or graphite flakes or ferrite and graphite flakes. These graphite flakes form as a result of higher carbon silicon content in grey cast iron, which provides also high fluidity. So, graphite flakes are present in this sort of flaky form, and they are present in this ferritic or perlitic matrix. The problem with these flakes is that they have sharp ends. As a result, they reduce the ductility and tensile strength of the grey cast iron. Then second form of cast iron that we studied was malleable cast iron, which is derived from white cast iron. It's just that it's cooled slowly or in a moderate fashion. So, again you can have perlite plus graphite rosettes or ferrite plus graphite rosettes. So, instead of flakes you will have irregular nodules of graphite in the matrix of perlite or ferrite. They have better machinability, better ductility and better strength as compared to grey cast iron. And then we looked at nodular cast iron, which have some amount of calcium, magnesium or cerium in there to improve the properties. And what they do is that basically they make the, so in this the graphite is present in this sort of irregular rosettes, okay, and here graphite is present in the form of nearly a nodule. So, this is graphite nodule and this is a rosette. So, this is basically a irregular sort of. So, what we will do in this case, in this lecture, is that we will look at some common non-ferrous alloys, and we will mainly look at copper zinc alloys, which is called as brass. We look at copper tin alloys, which is called as bronze. So, depending upon composition you can have variety of bronzes. We will not get into types of bronzes, we will just look at the phase diagram and some of the reactions in that. And then you have then we have aluminum copper alloys. So, phase diagram of aluminum copper alloys, and then we will look at so basically we are looking at the phase diagrams and microstructures, and then we will look at some TiAl alloys. So, these are the 4 systems that we will look at from the perspective of non-ferrous alloys, and these are all engineering alloys, very useful alloys. So, let us begin with brass. Brass is basically, you can say, it is a copper zinc alloy, and here copper has a melting point of 1083 degrees centigrade, zinc has a melting point of 419 degrees centigrade. As a result of large difference in the melting point, the system has a lot of peritectic reactions. So, as a result, the phase diagram shows significant amount of peritectic reactions and intermediate phases. Due to presence of wide difference in the melting points, and they have different structures as well. Copper is FCC, zinc is HCP. So, as a result, they have different crystal structure as well. So, there are basically 3 compounds. First phase is the alpha solid solution, which is essentially, you can say, it is a FCC copper with some zinc, and then you have beta phase, which is essentially you can say BCC structured CuZn phase in disordered, or it could be just CuZn ordered phase, which is cubic. Okay. So, basically this there is a transition that happens in beta to beta prime. Beta phase is a ductile phase, and this beta prime phase, which is cubic, is a hard phase. So, beta to beta prime transition happens at 465 degrees centigrade when it undergoes a order disorder transformation. So, let us look at the phase diagram of brass first. So, this is the phase diagram of brass that you can have a look at. So, you have on the y axis melting point. So, 1080 roughly 1083-1085 degrees centigrade is the melting point of copper, 420 degrees centigrade is the melting point of zinc, and there are a lot of phases. There are terminal phases alpha and eta. Terminal phases means terminal solid solutions. So, this is alpha, and the another terminal phase is this eta, which is zinc rich phase. So, terminal solid solution means zinc rich or copper rich phase, and then we have intermediate phases. So, we have this beta here, then we have gamma phase field, which is here, and then we have delta phase field, which is somewhere here. Okay. And then we have eta phase, which is here. So, there are quite a few phases in this phase diagram because of sharp differences in melting point and structure. So, we know that copper is FCC and zinc on this side is HCP, and they have huge difference in the melting point, although their atomic sizes may not be very different, they are very close to each other in periodic table. There is a peritectic reaction at 903 degrees centigrade for zinc. So, this is at about slightly more than 40% of zinc, and this is first peritectic reaction that happens in brass. Okay. And then so it leads to formation of, so you have liquid plus alpha, this liquid plus alpha leads to formation of beta phase. Then you have another peritectic reaction at 835 where liquid plus beta result in the formation of gamma phase, and then you have another peritectic reaction, you have another reaction at 700 degrees centigrade, which leads to formation of gamma phase, and then you have another reaction that leads to formation of eta phase. So, you have a lot of these phases which are present in this phase diagram, and the sequence of sequential peritectic reactions in this phase diagram. The usefulness of copper zinc alloys is basically in compositions up to about 40% of copper. Beyond that, copper zinc alloys are not very useful, but up to about 40% of copper zinc alloys have high lot of engineering applications. So, let me for instance so here for example, there is a transformation from beta to beta prime. This is at about 465 degrees centigrade, and this beta phase of copper transforms to beta prime phase, and alpha beta alloys of copper contain this beta prime phase, and this beta prime phase is a hard phase, and which is what provides strength to copper alpha beta alloys. So, the beta phase is cubic based. So, this is beta phase in which this happens at 50 Cu is to Zn 50-50, and for this phase you have each atom in disordered form is 50% copper and 50% zinc, which means there is a probability of equal probability of occupation of each of the sites. So, this is called as BCC structured. Okay. So, this is the disordered form, and it transforms to beta prime, which is ordered phase, where CuZn makes a cubic structure similar to BCC, but not BCC. So, this atom for example could be copper, and this atom could be zinc, whereas in this case 50% copper, 50% zinc. Right. So, this is what is basically the transformation that happens at about 50% copper, 50% zinc, and this is what is evident in the phase diagram. It transforms from beta to beta prime phase, from disordered to ordered phase. So, there are two microstructures of brass which are very common. Brass has so one is alpha brass and second is alpha plus beta brass. So, alpha brass is basically, you can say, it's copper rich compositions, and beta brass is has a composition. So, for example, you can have 70-30, 70% copper, 30% zinc. This is all weight wise. This is alpha brass, okay, and the beta brass would be somewhere around, let's say, 60% copper, 40% zinc would be alpha plus beta brass, and they have very different microstructures. Okay, so what you would see in alpha brass is, so let me just go to, yeah. So, if I go to microstructure, this is the microstructure of copper 70 zinc 30 brass, which has 30% of zinc, 70% of copper, weight percent, and basically it is a recrystallized sample. It has a lot of annealing twins. These twins form on 111 planes of copper, and they are present like these facets within the grain. So, you can see, for example, this is a twin, this is a twin, you can have a lot of other twins. For example, this could be a twin. So, these are twins. So, a lot of these sharp faces, twins form as a result of annealing, and this is a manifestation. This is basically a single phase alpha. So, matrix is basically alpha, and these are twins forming within the alpha phase itself. So, this is the typical microstructure of alpha brass. You can see the grain size is the order of about 50 to 100 microns, and this is one important alloy of copper zinc. Second alloy which has higher strength, that is in copper zinc, is essentially, you can say, is alpha plus beta brass, and this alpha plus beta brass has it's a air-cooled microstructure, which shows Widman-Staton kind of microstructure, in which alpha phase precipitates in the beta matrix. And so, if you look at the phase diagram, for example, this is 60-40. So, if you go to phase diagram, 60-40 would be somewhere here. Okay, so this is 40%. This is 40%. So, it should be 100% beta, but what happens is that some amount of alpha precipitates, and this is alpha plus beta prime. So, this is a two-phase region in which this alloy is made. So, you start from single phase beta. So, this is single phase beta, and as you enter into two phase beta, the alpha phase starts to precipitate out. And when you air cool it, you start forming this alpha phase. These bright plates are of alpha, and these are interpenetrating plate kind of network, needle kind of network of alpha and beta. So, this could be beta, and these are alpha phases. So, this is like an interpenetrating phase network of alpha and beta phases. So, this is alpha plus beta brass microstructure that you typically see. Now, in copper alloys, so as I said that, so if you draw the useful part of the phase diagram, so you have this peritectic reaction, first one, right, and then you have, let's say, so I am just zooming it up a little bit. So, this is another phase field. So, you have liquid plus alpha, this is alpha plus beta, and then you have beta phase field. So, beta phase field goes very narrow somewhere here like this, and you have then transformation from to beta prime alpha plus, and this is about 47%, and this is about 37%, and this edge is about 45%. So alpha and beta brasses lie between about 37 to 45%. So when you plot so this is temperature and percentage zinc. When you plot within this range the tensile strength and ductility, so between this two phase region, so if you plot tensile strength, for example, the tensile strength achieves a maximum in this region, whereas ductility has a maxima somewhere here. So you can say this is tensile strength, this is ductility of brasses. So correlation of microstructure versus mechanical properties. So this is what you have in brasses. So that is why the knowledge of phase diagram is important, because if you know what kind of phases are present, beta phase is stronger than alpha phase. So if you want a strong brass, you go to alpha plus beta brass. If you want a softer brass, then you go for alpha brass. Similarly, so just like you have in brass system so this is again an image of alpha brass 7030. So this is not recrystallized. So this is recrystallized, this is not recrystallized. As a result, you don't see the annealing twins. This is another image of 60-40 zinc. So you see these plates. So one is of alpha, another is of beta. So it's a Widman and Staten kind of microstructure of alpha and beta. This is again a alpha beta brass 55-45. So you can see that this is beta matrix and you have alpha needles. Now second microstructure which is important in this series is the copper tin phase diagram. Copper tin is called as bronzes. So we have second phase bronzes. Bronzes are basically copper tin alloys. There are a variety of bronzes such as phosphor bronzes and variety of other bronzes. Okay, so I'll just go to the phase diagram first before we go to details. So again, in this phase diagram, you can see that copper and tin have very vastly different melting points. As a result, they also have a lot of peritectic reactions. So you have first peritectic reaction here at 798 degrees centigrade, another one at 755, another one at 640, and then another one at 415 degrees centigrade, and then you have a eutectic at about 232 to 227 degrees centigrade. So 415 up to 415 you have peritectic, and then you have a eutectic reaction. So again, you can find the two phase fields. So this is liquid plus alpha, this is liquid plus beta, this is beta plus gamma, this is alpha plus beta, and then again you have delta phase field. So you can have gamma plus delta, you can have alpha plus gamma. So this is alpha plus gamma, this is gamma plus delta, and then you have alpha plus delta, and then you have another phase field, perhaps alpha plus this particular phase, eta phase. So you have eta phase, and so you can keep on labeling. So this would be liquid plus gamma, and this would be liquid plus epsilon, and this would be liquid plus eta. So it also has a lot of phases, and these phases have different, many of these phases have different mechanical properties. So as a result, bronzes are also you don't go to all the way to 100% tin. Typically, bronzes are less than about 10% or so. So bronzes are in general bronzes contain about 10%. So if 10% of tin. So if you look at the phosphor bronze contains about 1 to 11% 10 1 to 11% tin, and it contains some phosphorus, about 0.05 to 0.5% phosphorus, because phosphorus is present in castings as a deoxidizer. So, as a result you have these phosphor bronzes. So, if you look at some of the microstructures of bronze, so this is for example copper 21 tin 79 weight percent peritectic transformation. You have a microstructure which consists of so you have a eutectic mixture of tin and eta phase, and then you have the first forming you have the eta phase that forms, but this formation of new phase prevents the formation of the old phase, that is epsilon phase. So, a lot of epsilon phase is retained. If you go to phase diagram, for example, this is 79 weight percent. So, we are standing somewhere here. Okay. So, ideally speaking you should have only so this is your tin, and so we must have Sn plus eta microstructure, but what we have is some epsilon retained. And now what happens is that as you start cooling, so epsilon phase you will have liquid, and epsilon region you will have formation of liquid and eta, but there is no complete transformation, because once the eta phase forms, the further growth or further transformation of epsilon phase is stopped because of solid state diffusion that has to occur across the eta phase. As a result, in the final microstructure you have epsilon phase that is retained. So, you see a microstructure which is eutectic of eta plus tin with needles of with these eta phase and needles containing core of epsilon phase and periphery of eta phase. So, this happens because of non-equilibrium cooling, because a complete phase transformation does not happen. And if you look at the effect of strength, effect of tin addition on the strength of copper. So, as we keep adding tin to copper, so at about so you can see the first one is alpha phase. The alpha phase strength is somewhere here. So, tin addition to copper leads to decrease in the strength, but then you have a spike in the strength at this composition where you form these delta and eta phases, which is Cu3SN8 and Cu3. So, Cu31SN8 sorry Cu31SN8 not Cu3 is the delta phase that leads to formation of intermetallic compounds within the matrix, and it gives rise to strength in these tin alloys. And then you have other phases like epsilon Cu3SN, eta Cu3SN2, and so on and so forth. So, you can see that if you want high strength, you have to be around roughly around 20% of 10 to 20% of tin. So, you can see that within this you have to be somewhere here to achieve high strength in the. So, this region is what is the important region for bronzes. So, you have lot of bronzes that are present in case of so you have tin bronzes, you have silicon bronzes, so you have so we have lot of bronzes, we have phosphor bronze, we have tin bronze. So, this is basically tin bronze is the phosphor bronze. Okay. And then we have silicon bronze, silicon bronzes basically contain basically you can say it's a copper silicon alloy. Okay. So, copper tin alloy is this tin bronze, and this silicon bronze is copper silicon alloy. So, a variety of these structures, and basically in this let us say 10% bronze alloy, 10% tin copper bronze shows essentially then delta you can say particles in alpha matrix. So, if you have alpha and delta mixture, as I showed you that as you add tin, the delta phase has high strength. So, if you have delta phase present in the alpha matrix, it provides strengthening. So, high strength is obtained when you have this mixture of alpha and delta, and this leads to high strength in tin bronze. So, this is about the bronzes, and then we look at you can say aluminum copper alloys. again very useful engineering alloys, aluminum copper alloys. So what you have in this, it's a very complex diagram, aluminum copper diagram. So you again have, you know, the beginning up to about 50% you have this eutectic phase diagram. After that you have a series of peritectic reactions, because again you can see aluminum has a melting point of 660 degrees centigrade, and then it has melting point of 1084 degrees centigrade, 1085 degrees centigrade copper. So system is quite complex, it has a lot of intermetallic phases, but this is what is the useful portion of the alloy. Aluminum copper, aluminum some copper, is about 4-5% copper is the useful part. So essentially what you do is that you take about 4% copper, start from liquid phase and then go down all the way. So depending upon how you cool and at what temperature you heat treat, you can make very strong alloys. So these are aluminum 4% copper, for example, are, you can say, age hardenable alloys, and this hardness comes because of theta precipitates. So you can see these theta precipitates. The theta precipitates also go through formation of variety of stages. So you start from GP zones, which goes to theta prime to theta double prime and then to theta. So we don't want to form the final phase theta, we want to stop somewhere at theta double prime or so. So what you do is that you take a composition, solutionize it in this range and then cool it to lower temperature and then hold it at certain temperature here, so that you can form the precipitates, and then again cool it so that you stop the phase transformation kinetics completely. So again the knowledge of phase diagram is important, where you want to be and at what temperature you want to solutionize, at what temperature you want to cool to achieve the phase transformation. So this is again a very important material, aluminum copper alloys, which is useful for. So this is, for instance, the few microstructures. So this is aluminum 4% copper aged. You can see precipitates of theta phase within the aluminum matrix. So these black ones are the precipitates of, so this is aluminum matrix alpha basically, and then you have these theta precipitates. It could be theta prime or theta double prime. We can have higher composition alloys, for example, hyper-eutectic and hyper-eutectic alloys. So they look like, you know, alpha aluminum plus eutectic mixture. So this eutectic looks like this. So you have these again parallel plates of two phases growing in eutectic mixture. Similarly, you have titanium aluminum phase diagram, which has again lot of complex reactions, because titanium is a high melting point material, aluminum is a low melting point material. Again it has complex phases. The two most important phases are alpha phase and beta phase in titanium, and they form a lot of intermetallics like Ti3Al, TiAl, TiL2, which are very hard phases. So you can engineer titanium alloys by knowledge of this phase diagram. So for instance, if you have this alpha beta mix titanium alloy, which has so alpha phase has a hexagonal close path structure, beta phase is a BCC structure, and mixture of these two provides good properties in alpha plus beta alloys. So these are titanium 6 aluminum 4 vanadium alloys. So 6% aluminum, 4% vanadium, and this kind of microstructure is again alpha beta interpenetrating microstructure called as Widman-Staton microstructure. So again they are useful alloys from the engineering perspective. So these are some microstructures that we wanted to look at from the perspective of phase diagrams of non-ferrous alloys. So what we have learnt is about various non-ferrous alloys phase diagrams such as brass, bronze, aluminum alloys and titanium alloys. In the next lecture now what we will do is that we will look at the methods to determine the phase diagram, binary phase diagrams, followed by in subsequent lectures about the ternary phase diagrams. So thank you very much.